an actual problem. We have a wheel, we have a weight attached to it, we let it go, and it's the wheel is spinning, the weight moving down, plus we even adding friction to it. Well, so you need to draw your diagram, I need to draw my diagram. Again, theoretically, we should include normal force acting on the wheel, force of gravity acting on it. Now, what is happening to the wheel? It spins. It should have a clockwise angular velocity. This is what our everyday life experience and common sense should tell us. And if it doesn't tell us that, we should practice more to get that experience. If we just let the weight go, this string should make this wheel spin in the direction of this torque, and this torque is clockwise, so it should spin clockwise, and it should spin faster and faster, so the angular acceleration also should be clockwise. However, because we have a flexibility, right, we can choose the axis right here, bless you. Our rotational equation is really, really simple. We need to add torque of friction. How would torque of friction be direct? Friction always opposes motion. If I move it to the left, friction points to the right. If I move it to the right, friction points to the left. If this spins counterclockwise, friction acts clockwise. If it spins clockwise, friction acts counterclockwise. That's what it does. Friction always points opposite to velocity. So torque due to friction should point opposite to omega. Now we are ready to write the law, Newton's second law for rotational motion for this wheel. Okay, the object number one. In general, just write it like this: net torque equals this product, and net force equals this product. Newton's second law number one. Number two, of course, the second one will be applied to the weight moving down. Newton's second law for rotation for this wheel. So theoretically, we should write torque due to normal force plus torque due to gravity plus torque due to friction plus torque due to tension has to be equal to this times this. Or we can drop the arrows. You see it? No arrows anymore. But now what do we have to? Must write that symbol Z, which represents the component relative to Z-axis, which always points at you out of the screen. This is the direction of Z-axis. And relative to this axis, located at the middle point, this is 0, this is 0. Any questions? Why? Do you have a question? The green dot is the axis. The yellow arrow is the force, and we are calculating the torque of that force relative to that axis. Why the torque is 0? You have to say something specific about some specific variable, which is a part of a calculation for the torque. The magnitude of any torque is equal to, we have three options for that. Force times distance, force times lever arm. That's enough already. So why is this 0? Because R equals 0 or L equals 0, the same thing. There is no distance between the point of application and the axis. Now, plus, friction actually provides positive torque. It acts counterclockwise about that axis. Plus, because we're adding components, but this component will be negative, and the magnitude is force times distance from the point of application to the axis of rotation times the sine of 90 degrees. You can call it R, you can call it L. In this case, again, when everything is perpendicular, there is no difference. And finally, that has to be equal to inertia for the disk is 1/2 mr squared times, in my equation, this variable alpha now represents the magnitude of angular acceleration, but I have to choose a sign, a plus or a minus. Yes, that is the Z component. Well, this is what I'm asking right now. Z component of acceleration could be positive or negative. We have to make a choice. If we make a wrong choice, everything goes wrong. Z component of the acceleration, well, it's a number, so in general it could be a positive number, 0, or negative number. We have to make a choice, and it has to be correct. Please tell me, what is your choice? Z component is, well, it's a component of this vector that represents torque or acceleration or angular displacement or angular velocity. All those vectors point out of the screen or into the screen, and there is a common agreement for rotational effect, rotational motion, even possible rotational motion. Directed counterclockwise, Z component is positive, that's the rule. If it's clockwise, Z component is negative, that's what it is. So this is the relationship between these letters and this axis. Counterclockwise means Z component is positive, clockwise means Z component is negative. So what should I choose for z component of angular acceleration, a plus or a minus? Minus, minus. So what do? That's what we do. Now, another minus here. No one said anything. Now we are done with this equation. Torque due to tension is also clockwise. Everything clockwise has a negative z component. Number 2, we just have to copy an equation from a previous slide because we know what's happening. This is the y component, tension, gravity. It's moved down, acceleration has to, in this case, point down because it travels faster and faster. So tension is positive, gravity is negative, acceleration is negative. What do we do now? Copy these equations. So, oops, wrong. The torque due to friction minus the torque due to big R, little r, doesn't matter. Now I start using big, should be equal to 1/2 times big mass times the radius squared times this. That's the first equation. I'm not simplifying. I'm not so smart to do two things at the same time. My operation now is copy. That's what I'm doing. That's it. I just copy it. T minus mg is equal to m times negative y. I finished my operation. Now I can start thinking about, can I make it simpler? Every time when we finish a step, this step is done. Are we done? No. We ask a question, what can we do now? We start looking for additional connections. So this is another additional connection. But there is one more important connection which is not given to us directly, but we have to use it. There is something important we've been saying about the string, any string, again and again and again. It has no mass and we cannot stretch it. What does it mean? It means the motion of this weight is coupled with the motion of this wheel. How? Well, if this weight travels down by 1 centimeter, this point should travel counterclockwise by exactly 1 centimeter. If I had a spring instead of a string, we couldn't couple. But now, distance traveled by this weight will be equal to distance traveled by any point on this rim in the same time. Any questions on this? Now, we can relate everything else. Distance over time is what? Speed. So they should have the same linear speed. Picture number 1. Some point here. The picture number 2. This is lower and travels this distance, well, delta y. So this point will travel delta s, which will be equal to delta y. That's it. Divided by time, the linear speed of the weight should be equal to linear speed of this point P. But delta v over time, hence the linear acceleration of this point will be equal to tangential acceleration of the weight, tangential acceleration of that point P, tangential, the acceleration that is responsible for how fast speed changes. This is very important. If you have any questions on this, please ask now or on an office hour. But this is the connection we want to use. It comes from here, from this important relationship. But now what can we say? Well, this is just A, the acceleration of the weight, but tangential acceleration is related to angular acceleration. Now I'm using big R. So we've got one more relationship. Now we have 4 equations, but we can simplify these equations rather quickly, and that has been done. And I strongly advise you to do it at home as well and compare with this.